All right, everyone, welcome and thank you for coming to my talk today. Today, I will be introducing a new defense to shield classifiers against adversarial attacks. And this is, my name is Jonathan Russert, and this is work with my advisor, Dr. Padmini Srinivasan. And so, first of all, why even look into this work? Well, imagine we have a company which likes to use sentiment classifiers to gauge how well its products are doing online by looking at different mentions of its products or different reviews and analyzing that text to see what the general public feels like. Then we might have some competitor who comes along and wants to sabotage that company. So the way they can go about this is changing this text, and they will change this text so that it will look the same to humans, but what will end up happening is it will cause the sentiment classifier to incorrectly classify that text. So it changes so many words, and these words generally can be like out of vocabulary words that the sentiment classifier may not have seen before, so it cannot classify those words as well. And so once it changes enough of that text, then what happens is the sentiment classifier now cannot correctly classify that text. And this is a problem for that original company who now have wasted that time and money on this classifier. And it's no longer giving them back the feedback they need. So now we have shielding, which comes in, and where shielding is trying to do here is, even though we have this text, which is causing the classifier to produce the incorrect label, once we apply shielding, what we like to happen is, even with this adversarially attacked text, we are able to infer the correct label. And a motivation for our strategy stems from an observation that a lot of state-of-the-art attacks, adversarial attacks, aim to modify a minimum amount of the text. So this table here is actually from a state-of-the-art attack, bird attack, which performs well. And this red column shows they highlight the amount of text they perturb. And they're proud of the fact they perturb such a small amount of the text, because when you're attacking a text, the more you perturb, the more chance that you're going to create less readable or text that differs from the original meaning. And so from this observation that the state-of-the-art attacks modify just this minimum amount, our thought was then, well, why not just classify all of that portion which wasn't perturbed, which wasn't changed? Because if they're only perturbing up to 20% of those text, then there's still 80% of that text which hasn't been perturbed, hasn't been attacked. And so maybe the classifier then can still infer the correct label from that text. Unfortunately, we don't know exactly which text has been perturbed. So instead, what we do is we propose a strategy called sample shielding. And so instead, we take a random sample of that text, a smaller percentage of the original text, and we classify that sample. And since a single sample might still include those words or might not have enough information to make the correct classification, we repeat this process K times and then have these K decisions vote on the final decision for the label. So let's look a little more visually how this process works. We have some input text, and we actually explore two different sampling steps, two different ways of sampling. One is called sentence sampling. So in this case, we keep all sentences intact. So for example, if we have 10 sentences and we sample 30% of the text, we'd end up with 3 sentences for that particular sample. The other sampling process we look at is word sampling, and word sampling, we don't keep the sentences intact, but allow for any words to be sampled. And as we can see, this is done K times. so K different samples at that P percentage. And these K samples are then sent to a classifier, and we get probabilities for all those different samples. And one way we look at is, as I said earlier, we take just a majority vote of the labels for those K samples, and that leads us to our final prediction. We also experimented with taking these probabilities, sorting them, and training a simple neural net summarizer with the idea that maybe that neural net could observe something that we naturally couldn't observe. I don't expand on these neural net results today because generally we found that the majority voting did outperform that, but they are all in the paper, so I'd recommend you looking at them there. And so that's our method. So let's quickly look at what kind of threat models do we examine. Specifically, what does the attacker know about our defense and about the classifier? Well, we look at the threat model in this way. We say, well, the attacker is trying to attack some website, and now this website has a classifier which is uses to automatically classify different text. Now, if the attacker tries to send hundreds and thousands of queries directly to the website where there's just minimal change, this might be very easy for that website to detect that it's something fishy is going on. So instead, the attacker is going to have its own local classifier, which it will perturb its text. And once it feels it's ready, it will then deploy it to that website. And we look at two different threat model scenarios. One, the attacker does not know that the website has this sample shielding. So it's attacking the same classifier locally, but it doesn't have sample shielding for any feedback in that process. And the second threat model is when it actually learns that it's using sample shielding. So it incorporates that in its own local feedback as it's changing its text. So our experiments, we look at 3 different data sets that have been examined in attacks, adversarial attacks. 2 of them are sentiment binary tasks, that's the IMDb and Yelp. And then we look at a 4-class problem as well with AG News, which is different news articles. We also look at 3 different types of classifiers. We look at the BERT base, but we also look at CNN and LSTM to show that since this method is happening all at inference time, that it can also be applied easily to simpler methods as well. And we experiment against 4 different state-of-the-art attackers who have shown great results and being able to successfully drop accuracy of systems in previous years and still maintain the meaning of those texts. And for our experiments, we leverage a module called Text Attack, which has implementations of a lot of these attacks available. So it's very useful to be able to run and produce attack text and build on top of. And we look at 2 specific evaluation methods, accuracy and attack success rate. And as can be inferred, the classifiers want high accuracy, so the attackers are trying to drop that. And as they drop the accuracy more from that original, then the attack success rate goes up, or ASR goes up. So the attackers want that lower accuracy and higher ASR, where the defense wants to prevent that and bring back up that accuracy and drop the ASR. So these, we have giant table results for the very first threat model because we have all sorts of combinations. And this is the first threat model where the attacker does not know of the sample shielding, so it's attacking that classifier locally. And then the website is employing sample shielding during its classification time. Some quick observations as expected, just on the unattacked text, BERT naturally stands out and outperforms the other 2 systems across the data sets. And we also see that the attacks are able to cause great drops because they have specific access to those models. And so it goes from around very high accuracy, 90 to 100% accuracy in cases, all the way down to 0 to 1% for those attacks. So attacks are very effective, but when we apply the sample shielding, we also see that is effective as well. So the specific case I am pointing to here, this is on the IMDb data set, and originally the accuracy of the BERT model was 91%. During the attack, it got dropped down to just 1% accuracy, so it's an ASR of 99. But when we apply sample shielding, we're able to bring that accuracy back up to 78% and drop the attack success rate down to just 14. And this is consistent across the data sets as well. This is another example from Yelp, where it drops it down to close to 15% accuracy, but where sample shielding is able to bring it back up to close to 80. And it's true across models as well. So this is on the AG News data set, and CNN, we also see similar effectiveness. And other observations for the CNN and LSTM, the word sampling does better, which kind of makes sense with the way they're trained. And so we look at, you see this both for the, like I said, LSTM and CNN. Again, these are just different drops. We're able to really bring up that accuracy with shielding. For BERT, the sentence shielding is better than the word, and that's because BERT is much better using that context in there. However, that's also dependent on the average length of those actual text. So IMDb and Yelp are much longer text for classification compared to AG News. So when we get down to AG News, what happens even for BERT, is that all of a sudden, when you get down to short text, we don't have sentences to actually sample from. And so we don't have to sample from, then we're always going to be grabbing from those perturbed text. And so our accuracy drops a lot, but sampling is still effective for the shorter text. For the second threat model, where the attacker knows of sample shielding, we also see sample shielding is effective in this case as well. So we see some of the same observations where without the shielding, it was able to drop the accuracy greatly. But now, even with sample shielding in there, it actually causes the attacker to have a harder time. And this is because the attacker in these cases are using feedback in form of probabilities back from the model. And so when they're making changes, they're using these to guide their text. Now with sample shielding, recall that we take random samples. And so these random samples are going to change each time. So each time that attacker is querying the classifier with sample shielding, it's slightly going to get slightly different probabilities back. And so one case, it might think it's actually defeated that classifier, sends that text off, and it turns out another way of sampling actually didn't fully defeat that classifier. All right, so just to summarize up, there's a lot more analysis of sample shielding in there. So do check out that paper, as well as ask any questions in a second here. Some current limitations as well as future work, complete comparisons with other state-of-the-art defenses are currently limited. We kind of look at high-level comparisons, which show that we're in the same range, but future work will add those in. I'll also like to explore other tasks like natural language inference, where those texts get even shorter than what was shown here. So that could cause problems and show more limitations with sample shielding. And finally, now that even we see that this is causing problems to a lot of state-of-the-art attacks. So are there ways that we can modify those attacks, or those ways those attacks could be modified to actually defeat these randomized defense or given this randomized feedback? All right, that's all I have today. Thank you for coming, and let me know if you have any questions.
Time for one quick question. So I think on your final slide, you talked about some of the limitations. It feels like the sample shielding approach is only really applicable when the output is predictable from multiple parts of the input text. Right? If there's like one key sentence in the input that you can't predict the label without, then this approach may lead to unexpected results. Have you thought about that? I mean, there's several tasks, like for example, multi-hop QA or something like that, where dropping the sentence could just completely ruin the performance.
Yeah, so it's a good question, and I would, yeah, agree to it. I would definitely agree that that's one of the risks is when you're dropping it, and that was some of the idea of bringing in the case samples rather than just using one, because we don't know just with these smaller samples, are we going to grab enough information from that alone? And I think that so it could be a large limitation if you do need just a specific word or sentence, as you said, that gets dropped. That it might not, and that's the only one that's been attacked as well. That could definitely cause problems.
Great, let's thank the speaker again.